In this video, we're going to find out what the voltage on a transmission line looks like when a sine wave gets reflected. And I'm going to cut straight to the answer here. The sum of a right traveling wave and a left traveling reflected wave is a standing wave pattern. This rather hypnotic graph shows that. One wave is moving right, one wave is moving left, and the sum of them is standing still. To give this a bit more formality, standing waves are waves that always have their peaks and troughs in the same position in X. These positions are called nodes and antinodes. That's a weird behavior, but I can rationalize it in my head if I remember that the right-going and left-going velocities of the waves are equal and opposite. I think of the velocity of the component waves adding up, which makes the motion of the wave cancel out, resulting in a standing wave. By the way, this graph isn't a made-up example. This exact behavior could be seen in a transmission line terminated in an open circuit. Gamma in that case is 1, so the reflected wave amplitude is the same as the incident amplitude, which would result in these equal-sized sine waves running back and forth over one another. We'd like to get a good mathematical description of this standing wave pattern to see if it has any cool properties. To do that, we're going to find the voltage on a transmission line and then take its magnitude to get the shape of the standing wave envelope. I've drawn a generic transmission line up here to start that process. It's driven by VZP e to the j omega t, which is an analytic representation of our input voltage, plus a little phase offset that we're going to talk about in a second. I've made one sneaky change to the transmission line, which is that the load is now at position 0 and the source is at position -s. This change makes it easier to measure changes relative to the point of reflection. Specifically, it means that setting x equals 0 in the line voltage will tell us the behavior at the load. We've also arbitrarily chosen to define the load as having 0 phase, which means that we need to add a constant phase offset to the input, so the phase picked up over the line adds to 0 at the load. This is just a choice of mathematical definition. It doesn't reflect changing any of the physics or design of the input source. We're going to start by noting the standing wave pattern arises from a general solution to the wave equation. So we write that v of xt is equal to the sum of right traveling and left traveling waves. Then we substitute in functions that represent the waves. We know the right traveling wave is going to be e to the j omega t minus kx because of our work with infinite transmission lines. Each point on the line has a phase-shifted version of the input source living on it. We could have instead used the propagation coefficient to produce the same equations. Each point on the line will be e to the minus gamma x multiplied by the input voltage. Finally, we know the left traveling wave is going to be generated by a reflection, so it must be gamma times the right traveling wave. We can do some factoring to reveal interesting behavior. First, we factor out the omega term to separate the time and space behaviors of the line. This results in the Vn of t time-varying sinusoid appearing in front of the line, offset by some phase. Vn of t is being multiplied by the divider between zs and zdp to represent the scaling in amplitude as the input wave lands on the line. Finally, we take the magnitude of v of xt to find the size of the envelope around our standing wave at every x. E to the jx has a magnitude of 1, regardless of the value of x, so e to the j omega t and e to the minus jkx fall out of our expression. Said another way, we don't care about these simple phase shifts when we're looking at magnitude, and that's good because our standing wave doesn't seem to have phase shifts in it that depend on time. The interesting term in the magnitude expression is this last one, which this guy here, which says that the wave envelope is going to be scaled by a factor that depends periodically on x. This factor has twice the wave number as each individual wave, so we expect 2 nodes in each wavelength of a single wave. That makes sense if you reflect on the velocity of the right traveling and left traveling waves again. They'll hit one another twice as fast because of their opposite velocities, resulting in nodes and antinodes coming twice as often in the standing wave pattern. If gamma is real, the maximum this factor can be is when e to the minus 2jkx is 1, so the largest value is 1 plus gamma. The minimum is when the e to the minus 2jkx is minus 1, so the smallest value is 1 minus gamma. Complex gammas will have some phase shift relative to the purely real 1 they're being added to, but they still can't add or subtract more than their magnitude for any phase of e to the minus 2jkx exponential. So overall, we know this factor is going to scale our input amplitude by at most 1 plus the magnitude of gamma, and at smallest 1 minus the magnitude of gamma. As a final comment, we included the source divider in this expression, and the source divider could be complex if either Z0 or Zs has an imaginary part, but it's still just telling us how much voltage gets onto the line at x equals minus s. So, in summary, the sum of forward and reverse sine waves is a standing wave. The envelope of the standing wave has twice the wave number of the waves being added, and the max value of the envelope is the amplitude times 1 plus the magnitude of gamma, and the minimum value of the envelope is the amplitude times 1 minus the magnitude of gamma.